Somehow, you come up with a mathematical theory, not knowing any physics, discover 2 decades later that it's being applied to profoundly describe the actual physical world.
Yeah.
How can that happen?
God knows. Yeah, but there was a famous physicist named Wigner, and he wrote an essay on the unreasonable effectiveness of mathematics. So somehow this mathematics, which is rooted in the real world in some sense, we learn to count and measure, that's kind of, everyone would do that. And then it flourishes on its own. But so often it comes back to save the day. General relativity is an example. Minkowski had this geometry, and Einstein realized, hey, it's the very thing in which I can cast general relativity. So you never know, and it is a mystery. It is a mystery.
So here's a mathematical piece of ingenuity here. Tell us about this.
Yeah. Well, that's a ball. It's a sphere, and it has a lattice around it, those squares sort of things. And what I'm going to show here was originally observed by Euler, the great mathematician, in the 1700s. And it gradually grew to be a very important field in mathematics, algebraic topology, geometry. And that paper up there had its roots in this. So here's this thing. It has 8 vertices and 12 edges and 6 faces. And if you look at the difference, vertices minus edges plus faces, you get 2. Okay, well, 2, that's a good number. Oh, here's a different way of doing it. These are triangles covering. Oh, this has 12 vertices and 30 edges and 20 faces, 20 tiles, and vertices minus edges plus faces still equals 2. And in fact, you could do this any which way. Cover this thing with all kinds of polygons and triangles and mix them up. And you take vertices minus edges plus faces, you'll get 2. Now here's a different shape. This is a torus, or the surface of a donut. 16 vertices covered by these rectangles, 32 edges, 16 faces. Hey, this comes out 0, vertices minus edges. It'll always come out 0. Every time you cover a torus with squares or triangles or anything like that, you're going to get a 0 when you take that thing. So this is called the Euler characteristic, and it's what's called a topological invariant. Now, it's pretty amazing. No matter how you do it, you're always going to get the same answer. So that was the first sort of thrust from the mid-1700s into a subject which is now called algebraic topology.